Well, thanks very much for inviting me to talk at this very interesting meeting. So, I won't repeat the title again, it's got all the right sort of things in it, quantum dots moving in surface acoustic waves and things that we can do with them. And lots of people have been involved, so Rob McNeil, Matthew Vinesh, particularly were involved in this work, and the people in this third, well, Sukan and Hang-Tian are here today, and with posters outside. So, when I put this logo for the SAW Train European Consortium training network that we have, and which is supporting this meeting, I didn't realize it was animated, so I've been looking at this just now and seeing how the electron suddenly gets bounced out over the hill. I don't know what the physics of that is, but it looks nice anyway. So this is the outline of my talk. So I'll talk about what we can do with quantum dots that are moved and created by surface acoustic waves moving along a channel that's defined by gates on the surface of a piece of gallium arsenide, and lots of different applications. And then I'll talk for a while about how we can transfer electrons between static dots, what we call ping pong, and then how we can make very rapid changes to the potential, some non-adiabatic changes to the potential that an electron is sitting in that cause it to get excited into higher states and then oscillate backwards and forwards within the dot. And that's because the SAW is moving past static changes in potential, which become therefore very rapidly changing potential change. And then I'll talk a little bit about our current work, which is trying to get photons out of p-n junction, but since we haven't succeeded very much yet, I won't say a great deal about it. So we start with a gallium arsenide heterostructure, as many people do. So we have a two-dimensional electron gas, or these days a quantum well, at this place about 100 nanometers below the surface. And so that's the blue region here, is a layer of electrons. It could be holes, or electrons and holes in different places. That's what we've just developed. And then we put gates on the surface, which here are just depleting out the electrons underneath. And if you put two such gates with a gap down the middle, and apply negative voltages to each of them, then that creates a very narrow channel down the middle. And so if you think about the potential, this is just a calculation of the potential with a little SAW going along it. Here's the sea of electrons at one end, here's the sea of electrons at the other end, and a narrow channel down the middle. We can change the height of that channel to deplete out the electrons completely, so then the surface acoustic wave is not screened there, and the potential that goes along with the surface acoustic wave in a piezoelectric material drags electrons along there. So it's a very flexible technique. We can make any shape of gates we like. I'm sure everyone knows, who wants to know, about how you make surface acoustic waves. So this is just a transducer on the surface of a piezoelectric material. Zooming in on the transducer, it's interdigitated, so sets of fingers, one with a high frequency voltage applied to it and the other grounded, and so that sets up an oscillating electric field that couples to the strain of the material, sets a wave, a Rayleigh wave, going along the surface, and we can then fire that to a place, say, a millimeter away on the chip. So here's a typical sample transducer at each end. We use one of those transducers at a time to launch a SAW towards the interesting thing in the middle. That might be the 1D channel I just showed you, but it might be something more complicated. So there's that sort of potential that the SAW drags electrons through there. And so if you look along that potential, we have a cross-section of the potential like this. So a sea of electrons at each end, a rise in the middle, and it's depleted, so there are no electrons there. So SAW comes along from the left here. It's a minimum that drags a few electrons out of the sea here. So it's screened within the sea over here. So the electric field, the potential associated with the SAW, is screened out here. So it's only at the edge here that it manages to become strong enough to actually drag some electrons out. We have no detailed calculation or proof of what exactly happens, but we know that it ought to be that it picks up a number of electrons, and then as the SAW potential collides with the static potential from the gates here, so as this maximum here and the minimum in front of it move into the region of the hill, the potential gets steeper, And so the SAW dot, this dot of that is confined by the SAW in one direction, the gates in another direction, and the growth in the other direction. So it becomes a zero-dimensional dot. It drags electrons up here, gets squeezed, loses electrons. So here are some electrons, some are being pushed out at elevated energy, but eventually the dot has a certain number of electrons in that don't get pushed out. So it's about halfway up that the potential gets so steep that that's the final number of electrons that survive. So as it goes through, those electrons that have survived that far go all the way through. So that should be pumping a current. So indeed, we can see what we call an acousto-electric current. And if I plot it in units of E times the frequency, so the frequency is about 3 gigahertz. And so we're pulling 1 electron through per cycle. So that should be a current of about 450 picoamps. And so each of these lines is spaced by 450 picoamps. And so we see, with no applied bias, just with the surface acoustic wave dragging electrons through the system, we see a DC current. And that current has steps in it. And the steps are at multiples of E times F. So we had hoped that this would be a current standard because it was so easy just to get a current, and then multiples of that same current. So you might be able to get very nice flat plateaus at 10 or whatever. You can see little wiggles on this plot. But that corresponds to 10 electrons or 2 electrons, so n electrons going through the dot. So they manage to survive because the dot's a bit bigger, because this axis is the gate voltage squeezing from the sides. So it makes the potential higher, but also makes the potential narrower across the sample. But if we zoom in on the first plateau here, on one of the best samples, it looks flat if you plot it in a particular way, but then when you zoom in, it's say 1 part in a few thousand really is the best we can do for accuracy. So that's not good enough, and there are better ways nowadays that have partly come from this sort of idea of pumping the electrons, moving the potential up and down. But these days they're done with a couple of gates rather than with a surface acoustic wave. So we turned our attention to thinking about what else we could do with surface acoustic waves and pumping single electrons. So we've got these dynamic dots. We now know that we can capture an electron and move it along. It doesn't have to just immediately come out the other side of the device. It could be dragged along a channel. And it could also be dragged uphill to a region where there are holes instead of electrons. So this is an idea we've been pursuing for a while now. And so this is a bit schematic, but the idea is that you have the conduction band and valence band in an N-type region, and likewise in the P-type region, and chemical potentials equilibrated on the two sides. So there's a large hill in between. But the surface acoustic wave can always provide energy to drag the electrons up that hill, provided that the slope is not too steep. If the slope is steeper than the steepest part of the sine wave, then it will drop the electrons. There won't be any minima there. So we've been trying to design this potential, and certainly we wouldn't be able to use as many oscillations within that distance, so it has to be a much shorter channel than that. But that's the idea, that if you had N-type and P-type next to each other, when the electrons get into the region with holes, the electron could drop down into the region with holes, recombine with any of those holes that match its spin, and give out a photon. And then the spin of the electron will be converted to the polarization of the photon. And so that should be a good way of reading out the spin of the electron. We'll hear later on, I think on Friday, from Tristan Meunier about how they try and measure the spin in a SAW-driven dot, but they're doing it 1 electron at a time. Here we should be able to measure a sort of flux of photons coming out, corresponding to the flux of electrons coming through this system. And so there may be advantages in each of those. So, actually that was my second item there, but if you can generate photons, 1 per electron that comes in, and you have 1 electron coming in at a time, that ought to be a single photon source. And so that will be a sort of sideline, an extra benefit of making some structure like this, that we can play with single photon sources. So quite a long time ago now, in 2000, Crispin Barnes in our group in Cambridge was thinking what else you could do with surface acoustic waves, and he came up with this idea that you can have a set of SAW channels, so single electrons in the SAW minimum, and a set of those in parallel. So think of the SAW wave as a vertical line here, and a number of channels defined maybe hundreds or whatever of channels defined in parallel, and the electrons in each of those SAW-driven dots are being dragged along their channel. And occasionally the channels are brought close together, so there's a tunnel barrier where it's shown in green, or some sort of magnetic changes, magnetic field applied in particular directions to manipulate the spin of the individual electrons. So it's rather schematic, it's a theorist's idea, and we have been wondering about whether we could really dare to implement it. I think we've been left behind by a lot of the other work that's going on static dots, but some of these ideas we've certainly played with and found rather useful. So if you take that sort of design and think, well, it's very difficult to make such a thing, here's something like that. So I showed just 2 gates before to make a channel. So that channel would be, say, somewhere here, where we've got 1 gate there and 1 gate here, and the dark strip here is the SAW channel. So we can quantize electrons here, just pump 1 electron in through that entrance, and then it gets dragged down this channel towards this region in the middle, and that region has actually 2 channels in parallel and a very thin tunnel barrier, about 40 nanometers wide, between the 2 channels. So in that region we have lots of gates on either side to vary the size of the channel in each place, to adjust the potential and so on. So when you see these little vertical gaps here, in dark lines here, they're so narrow that no electrons can get through, so that the voltages on the gates on either side pinch off completely. So we can treat those all as 1 gate, but with different voltages in different places. So that's very flexible. And we now have a tunable channel here and a similar one down here. And so in principle, there's a lot of flexibility, and we tried to go a bit further by having 2 channels and various sort of air bridges and so on. But that was never quite, with 25 gates or something, it was never quite working. So we haven't measured that one, but we've measured this in a lot of detail. But firstly, I'll talk about a simpler device where we can think about transferring quantum information between static dots. So I mentioned the static dots have got a lot further with quantum computing than we have with moving dots. So if you think about what a quantum computer might need, with its qubits, if those are the electron spin, so a 2-state system is spin up or spin down of the electron in a quantum dot, the things that are needed for that sort of quantum computer, you need to be able to move electrons or qubits significant distances to the next qubit or to some storage place, and to retrieve them, to move them back and forth from memory, or to move them, as I said, between qubits. So people are talking about the need to have quite a distance between qubits just so you can fit in the conventional electronics, maybe on a separate chip or something. So a 10 micron distance would be impossible to transfer electrons just using gates. So maybe there's scope for using a surface acoustic wave to transfer electrons. So how can we do that? Can we take an electron in a static dot here, send a surface acoustic wave pulse in, and move the electron along and capture it in another quantum dot? So that's what we've managed to do. And so our device is about 4 microns long, and we have a surface acoustic wave, well, a transducer at each end of the chip, so we can send a wave in from the left, move the electron from the left quantum dot LQD to the right quantum dot RQD, or we can do exactly the same in reverse, sending a SAW in from the right. And we haven't yet demonstrated spin transport, but you'll hear from Tristan Meunier from the group in Grenoble that they have done so. So with a very similar device. So here's the gate structure, lots of gates to define this quantum dot at one end. So that's looking at the potential. Here it's just looking along this channel. We can see a narrow depleted channel there. So no electrons anywhere in this system. Then a little puddle here which can contain electrons if we put them in there, and another one right at the other end here, and what we call plunger gates here and here to just squeeze the size of the dot. And then a sea of electrons on the entrance and exit from which we take individual electrons when we need them. But there were some questions in some talks yesterday about what the power of a SAW is. So what's the amplitude of the SAW actually in a sample? And so I just put in this plot, which is a measure of a quantum dot in the beam of a surface acoustic wave. This is not the same type of quantum dot, but what we can do here is see Coulomb blockade through a dot. So we have two leads and a quantum dot in the middle, quantized number of electrons in the dot, and just see how many, so do an ordinary measurement with DC bias. That allows you to calibrate the energy spacing and charging energy of the dot, of the electrons in the dot. And then we can apply a surface acoustic wave and see what happens. So if you think about minus 30 as dBm as the power of the transducer, that's very small. So basically no significant amount of power. And so looking along this line here, there's a feature, this is differentiated, so you see a white and a dark region every time there's a Coulomb blockade peak. So it corresponds to adding 1 electron extra every time we open up the dot a little bit, going from left to right here. So that's a set of Coulomb blockade oscillations. And then as you increase the power, we're moving the whole potential of the dot up and down. I can't remember what size this dot is, but there'll be a difference in the surface acoustic wave potential in the middle of the dot compared with at the barriers. And so we're really just moving the barriers up and down a bit. And so the spread, so each of these peaks spreads out corresponding to the displacement of the barrier from where it would have been before. So you've got a tunnel barrier on either side of the dot. So when the two peaks spread out and converge at this point, that gives you a measure of the energy change that the surface acoustic wave has brought about. And sorry? Yes, I think we're differentiating in the bias, the plunger, the gate voltage direction. So it's transconductance. Sorry?
Oh, okay, transconductance.
Yeah. So the point is, I don't want to labour this point, but you can see that at a certain power, minus 20 dBm in this case, there's enough SAW amplitude to actually bring two energy levels in the dot into alignment. So that corresponds to lowering the barrier a bit. So we can get an estimate of the SAW amplitude from this at very low power. So we tend to use much higher power when we're dragging single electrons along channels. But you can see here that there is a sort of expected relation between the SAW amplitude that we deduce from this and the power that we're putting in. Obviously, so there are some losses in the cables going down and so on, but it is a technique that could be used quite regularly if you wanted to quantify the SAW potential more accurately. And so we can look at the amplitudes for population and depopulation, but I won't go into too many details now. But going back to our pair of quantum dots, in this case we couldn't do that type of measurement because there's only one end that has a tunnel barrier. The other end of the dot goes into this channel, which we can't really do Coulomb blockade measurements in. So we can still detect electrons in the dot. So how do you detect an electron in the dot? This is something that Charles Smith in our group invented in about 1993, was to have a narrow channel beside a quantum dot. And that channel is in a totally separate circuit, so you can see this horizontal gate that goes all the way along there. That isolates the dot in the top part here from the circuit down below. So this constriction here is just a one-dimensional constriction, so it's very sensitive to the gate voltage nearby. You can squeeze it till it's almost pinched off and just measure the current or conductance through that channel. But if you were to add an electron to the dot on the top there, the electric field from that, or electrostatic potential from that electron added to the potential in this constriction here will be enough to change the conductance of that constriction. So if we look in this device, when we sweep this plunger gate to remove electrons from the dot and just measure the conductance, you see little steps as you push electrons out. So this sort of sawtooth picture tells you that you're detecting an electron jumping out of the dot. And when you sweep back again, so red is going down and then blue is coming back up again, mostly the peaks line up, but if you get down to very close to pinch off in the dot, it becomes isolated, and so there's a delay between getting rid of an electron and the electron coming back in again. It's actually, the tunneling time is comparable to the time you wait in the experiment. So what we can therefore do is go into that regime where actually the dot is completely isolated from the leads. There's an enormous tunnel barrier, and so when we put an electron in the dot, it will stay there. And then we Now look at the dot and how we can initialize it. So we know we have a potential which can hold electrons. So we scoop down into the sea of electrons on the left, bring up the gates and try and hold the electron, and then keep it in the dot, but it's now above the Fermi energy that there was in the leads. Or we can deliberately fumble the catch and sort of drop the electron on the way up and get an empty dot. But we've done the same gate operations, just in the wrong order. And so the electrostatic potential due to the gates is the same after both of those two, so we can compare them. But in one case we caught an electron, in one case we didn't. So looking at the detector, the blue line is a whole set of experiments where we deliberately didn't catch an electron, and the red line is where we deliberately did as a function of a gate voltage. And you can see a step which is where we caught one electron, or 2 electrons, or 3 or 4. So you can deliberately choose how many electrons you catch there. And there are different regimes where you squeeze too much and then you can't actually hold many electrons in the dot. So we initialize by taking an electron there and adjusting the dot until it's ready to fall out into the channel at this sort of place. So that just shows that we can detect accurately how many electrons we have in the dot. And so we prepare the channel, we initialize the dots. Preparing means actually sweeping out any electrons that got left behind in the channel, and the SAW is very good at that. It's a potential moving along. So the best way to clear your device of electrons is to send a SAW through it. And any that were trapped in shallow potentials get taken out. So then we fire a short SAW pulse across the device and detect whether an electron has moved from one of the dots to the other. So we start with an electron in one dot, and then the surface acoustic wave pulse comes along and drags it along and deposits it in the other dot. So we can then test that the device is working by, or doesn't have any spare electrons in it, by just keeping the dots empty and sending some pulses through. What I'm plotting here is the signal on the detector on the right quantum dot, or the detector on the left quantum dot. And in both cases, nothing's happening as we send a pulse in. So this pulse of SAWs comes in at this blue vertical line. The measurement is over a few seconds. The SAW pulse is over a few hundred nanoseconds. So rather different timescales. So we can't monitor what happens during the SAW pulse, but we can see what happens before and after. So nothing happens. We don't find any extra electrons if we don't have any electrons in the system. But if we do put an electron in the right quantum dot here, on the right dot we see one electron is in the dot, so that's what we call a 1 state there. The SAW pulse comes along and it goes to 0. And we can repeat this measurement lots of times, and so the SAW is capable of kicking an electron out, presumably into the channel. So then we look at the left quantum dot and see what happens there. And in some cases, like this first case here, we get nothing. So no change, no electron has arrived. But in other cases, most of the time, we get a sudden step. So corresponding to the loss of an electron on the right, we see an arrival of an electron on the left. So that shows that we've transferred an electron from here to there. Yep?
What's the efficiency of this process? What is that most of the time?
I mean, I think it all depends on how we've set up the gate voltages, but it's in, there are a few percent probably errors and things like that, maybe 5%, something like that, but I've forgotten the exact numbers. But I'll show you in a minute that we can play with a single electron very efficiently for quite a long time. So here's our SAW pulse coming from one end. So it's a very short pulse, and we can go down to about 20 nanoseconds. So we've designed our transducers to have a poor quality factor, so they can put through very short pulses. Normal transducers with lots of fingers and single fingers like this have a very narrow resonance.
What's the time of flight between the dots?
So it's a 300 picoseconds. So the speed of sound is 300 picoseconds in 1 micron, because that's the wavelength that we use. So it's about 1.2 nanoseconds. So if you're thinking about coherence and what will happen to the electron spin as it travels, that's a reasonably long time, but on some timescales it's short compared with the spin lifetime, we hope. So there are tricks we can play to make sure we get very short pulses. So then we have two transducers, so we can now say, well, we've transferred the electron from right to left. Can we send it back again? So here's a set of measurements. So we took, so each of these colored traces is a different consecutive measurement over a few seconds. So we start with no electrons in the system, just alternate the direction of motion of the saw, so from left or right, and nothing happens. That just proves that we've got a nice empty system, no electrons are popping up from nowhere. Then we deliberately put an electron in the left dot and kick it out with the saw, and it arrives at the other dot. Adjust the potential a little bit on the right dot because that was slightly harder to get electrons out of, and then fire it back, and it arrives, and fire it back, and so on. So you can see this sequence without any errors, and then deliberately leave the barrier down where it arrives, and so it falls out at this point. The dotted line there is just because the gate was in a very different configuration, that the detector wasn't working there. But then after that you just send the saw back and forth again and no further electrons. So that just shows that when we want an electron, it's there. When we drop it, it goes out and is lost. So we are really dealing with just one electron. So we've done lots of experiments to try to convince ourselves that it's not like Newton's cradle, that you push one electron in here and another flies out there, and it's just a rigid set of electrons in between that you're pushing backwards and forwards. So we're certain that's not happening. So someone asked about the reliability of the transfer. So what we can do is just send the electron back and forth as many times as possible. I think the maximum number of times we've managed about 60. So that's 30 times one way, 30 times the other way. So in each case, the electron moved when it was meant to move and arrived at the other end. So it's effectively an accuracy or an error rate of less than 2%. And the error in this case, actually, at the end of it, was that an extra electron joined the other electron. So presumably the saw actually pumped electrons from one of the C's on either end up a hill and into the dot, and so we could design around that in future. So having got this ability to transfer electrons back and forth, and the obvious next step is to try to initialize the spin of the electron and measure it at the other end. And so we thought it would be quite straightforward just to get the electrons to be emitted, to recombine with the hole and then emit a photon. Quite straightforward, but easier than other things. And so you hear the Grenoble group later in the week. They've taken the other tack, which is to initialize the spin and detect it electrically. And we're still going with the idea that we can detect it by detecting a polarized photon coming out the end, which will have other uses as well. So just got this graphic to show what the sort of uses of this transfer could be, that if you've got a cluster of qubits or a single qubit or whatever that you need to move some information from one place to another, you could either have a set of extra dots in the middle to adjust, to try and tip one spin from one place to the next, to the next, to the next. So bucket brigade or whatever to drag electrons along to the other cluster, and that's quite, over long distances, that's a very difficult technique. Or you could try and send a photon over very long distances, so that's where us getting our electrons to recombine with holes to give out a photon would be useful. Or you can use a dynamic dot as driven by the surface acoustic wave to drag your electron from a qubit here into a qubit there. So it may have uses in the long term like that. So that's one of the things we've done. And I told you that it was all part of the idea of thinking about what we could do with multiple channels and tunneling between them that might be useful for quantum information processing in some form or other. And so this is a device that I showed at the start, which is attempting to look like that. So instead of any static dots, we have just channels, and the saw grabs electrons from one place, drags them along the channel. So in principle, we're planning to have two electrons, one in each of these channels, and they're dragged along towards the middle, and then they can interact, and electrons in the two channels, if you've got a single electron in each channel, the electrons can tunnel through the barrier, and they might have swapped over. It's highly unlikely that two electrons will be on the same dot because the Coulomb interaction would be too strong, so that's out of the picture. But they might have swapped over, or they might not have done. So if that's a way of entangling those two electrons. So you can make a C0 gate from a couple of such constrictions, such tunnel barriers. So here we have very, very fine lithography, so a 40 nanometer barrier here, sandwiched between two other gates to make the channel, these two channels, to make them diverge like that, but to be able to apply a voltage separately to this tunnel barrier, separately from all the other gates around. And this gap here is deliberate to enable us to change this gate separately from that one. So very small features on here. So that's all that's going on in the middle there. So looking at the potential, there are two channels like this, both of which are empty. And we spent some time looking at the two electron case, one electron in each of the two channels. But we got engrossed in looking at some little oscillations that we saw when there was just one electron in one of the channels. And so spent a long time investigating that and trying to work out what it was due to. So here we have a calculation of the potential for such a case. So one of the channels is quite squeezed, the other channel is quite wide open. In fact, it doesn't matter for the oscillations I'll show you what the other channel is doing. So really we are just looking at an electron coming down here. The potential suddenly changes at this place. So it's traveling in one direction, then it suddenly changes direction, and the channel potential, the dot potential gets a bit wider at that point. So there's a sudden change in potential. And I mentioned it takes an electron 300 picoseconds to move along here. That's the sound velocity of the surface acoustic wave. So to travel past a feature that's a fraction of a micron long, then it's in the tens of picoseconds range. So we can make changes, I think, on down below 10 picoseconds as you go past different features of the potential. So just tell you a bit more about the measurements. So we start with the current coming in. That's what we measure coming in here. So we know how much current goes in there. We can measure the current coming out over here. That's this red curve. And when the tunnel barrier is open, these two don't quite match. So we can see the plateaus are at EF, 2EF, 3EF. But we're losing some of the current because it's tunneling out through the barrier. And we can control that. So that's our tunneling current. We can look at the tunneling current as a function of the barrier. So that's the tunnel barrier. And we can get the statistics of how likely an electron is to tunnel out. We can fit that to energy levels in the dot, tunneling out into a sea of electrons out here. So we can try to estimate the energy spacing between states when you have an electron, a single electron in the dot, or two electrons, or three electrons in the dot. I think the third electron is what we get is the change in energy between the one electron case and the two electron case is a few milli-electron volts. To the third one, it seems to be much higher, but I expect that's it's complicated by the fact the barrier is very, very thin at that point. But we can see the statistics, the tunneling probabilities of tunneling through that channel, that barrier. But what intrigued us was if we sweep the one of the gates, what we call the top center gate here. So the electron's coming down from the top left here, goes into this channel. But as we sweep one of these gates, it's not terribly important which, we see a particular characteristic. We're turning off the current coming out of the top here. So it's forcing current to come through the barrier. But we see little wiggles on there. You might think that's noise, but if we just differentiate that, we see a set of wiggles on there like that. And then we follow those as a function of the top left gate. So the top left will be up here. So we can vary different gates. This is the top center gate. And we can see that these wiggles do not go away. So they are very reproducible, and they vary in a particular way as a function of different gate voltages. There's some features we have no idea about, like this, which we haven't seen more of. So we modeled this using a time-dependent Schrödinger solver. So we think of an electron coming along that channel, having a slight sudden change in the potential, and see what happens. So what I'm going to plot here, this is the potential across the channel, so it looks like this. So here's our electron going into the board, dragged by the saw. Set of energy levels there. The wave function here has a chance of tunneling through this barrier out into the sea which is the second channel on the right. And in fact, I mentioned it doesn't have much dependence on that channel, so we leave the channel open actually, so it's a large two-dimensional system. So there's no dependence on the levels in this region. These electrons are higher in energy than the Fermi energy on the other side of the barrier, so there's no constraint on them tunneling out. So here we have the wave function of the electron as it comes along. This is zooming in on the tail here, which is going into the barrier, and this is the potential. So, and this is just this wave function plotted as a function of time on the y-axis and position across the channel on the x-axis. So we can see the electron comes towards the barrier, and suddenly at this point it's hit the edge of the barrier, the very thin barrier, so there's quite a lot of tunneling at that point. See a lot tunnels out there. Then it just oscillates back to the other side of the channel. You can see this oscillating to left to right, and then it goes off as the channels split again. So why does it start oscillating? Well, if you think about the change that suddenly happens at this point, the change is so rapid, it's non-adiabatic, that suddenly it is now in a new ground, well, there's a new ground state for this slightly wider potential. And so to describe the wave function, the initial wave function is a linear combination of the eigenstates of that new potential. So it's now in a superposition of, say, first and second states, so ground and first excited state. Any higher states will escape over the barrier very rapidly. So that's, I think, why you see a sudden loss at this point. The higher energy components of that get filtered out very quickly, but now you're left with just these two states doing an oscillation between the two as their energies are different. So if you sum these, you'll get the electrons on the left or on the right, and then that phase will change. And so every time that phase does change, so it oscillates periodically from left to right and back again. So this is what the wave function is doing. It's losing a bit of amplitude because it has a chance of tunneling out every time it comes close to this barrier. So that's the most of the probability tunneling out. Then every so often the probability gets greater because the electron is closer to the barrier, there's more of a tail in the barrier, and so on. So we get a number of bounces off the barrier. And so these are coherent oscillations, and we think, how does that get measured? What are we actually measuring? So here's our electron coming down, getting a sudden kick as the potential changes, oscillates back and forth, has a chance of tunneling each time, and we're just measuring the current, either that is lost to the top here or comes out of the bottom here. It doesn't matter which we measure. So we're summing over a number of bounces. So if you think, okay, maybe we start with 3 bounces and then we change a gate voltage. So as you change the gate voltage, you change the oscillation frequency. It's the difference in energy between the two states. So the rate of tunneling, of oscillating backwards and forwards in the channel changes. And so you might have time to fit in a 4th bounce. So you gradually, let's say, increasing the frequency of oscillation or decreasing the time between bounces, so that maybe we could fit in 3 before, now we can fit in 3.5. But 3.5 doesn't give you any change in the current. It just means that each of the bounces takes less time, so there's less time to tunnel, and so the current will drop. So if you look at the tunnel current, somewhere here you're on a place like this, and the current drops as you increase the frequency, because the time spent near the barrier decreases for each of the bounces. But then suddenly you manage to fit in a 4th bounce, because now the time is shorter per bounce, and so we can fit in 4 bounces. I'm drawing this as it's not likely to tunnel near the ends, because the tunnel barrier, due to fringing fields from all the other gates, will be thinnest presumably in the middle here. We don't know exactly how long this is. Yeah.
Can you see the difference if you add the tunneling events coherently or incoherently?
I think in the calculation this is added coherently, but I don't think it really matters, because I think each time these electrons come out, they go into a big sea of electrons, so it's very unlikely that they sort of stay together to overlap and add together coherently. But we've certainly not, in the experiment, we've not seen any dependence of the oscillations on what's happening on this side. So I think if it were coherent and we could reflect the waves back and forth with these gates, then we would see some effect there, but it doesn't seem to be relevant. So we're going from 3 oscillations to 4, but in the middle the current drops, and then it rises again as we fit in the 4th oscillation. So that's the reason we think for seeing these very small oscillations in the current. So we are measuring the fact that the electron is oscillating, but we're not measuring where the electron is. We're doing what you might describe as a weak measurement. So we're getting some information about the wave function without measuring its position. We're measuring the fact that it is oscillating, but we're not disturbing the system. It goes on oscillating even though we're doing this measurement. And so maybe there are ways of doing more interesting things with this now that we know that we can get some information from an electron oscillating in a dot. So we could prepare it in various ways. We could possibly set up multiple channels and see whether one channel can read out information from the other and interfere, well, act like a measurement by having 2 channels interacting in some way. But that's for the future. This is just checking that the gates that do what they should. So in the model, the lines as a function of various gate voltages go and have a particular slope, and in the measurement, the slope is pretty similar. So there's some calibration issues. Well, we don't know exactly how energy is related to the gate voltages in various cases. But from the simulation, we can see that there's a good match to what we see in the experiment. So we thought then, well, okay, now we can initialize and measure. Our device was just one barrier which did both things. So could we initialize and then measure downstream? So can we set off this oscillation and then see what happens later on? So we built a 2-barrier device, and we knew we didn't care too much about the bottom channel, and so we don't have a bottom channel here, but we have 2 regions we can tunnel into, and we can treat those separately. It was the same idea. Electrons come in from the top here and then go along and out the top. And so we can do the same sort of thing. We can see the current coming in blue and coming out in red as in the top here. So that's what we've seen before, but we've just duplicated it here. We can see similar oscillations, same idea. That's the current, that's the differential of the current. And so then we plot this as a function of various gate voltages and the plunger gate. So the plunger gate is the gate that's just above the barrier. So it's the one sort of pushing in like a sink plunger for this LP here or RP here for left and right regions. So when we look at the left dot, well, that was the left part of the channel here. I shouldn't talk about dots anymore. So electron comes along here. Exactly the same experiment as I've just described is happening on this region here. We have a current that we measure. If we filter that, which is effectively differentiating it, we see a set of lines. We have to be careful that the filter itself doesn't have some frequency dependence that introduces features, and so we're careful of that. And so these features are real, and so we've got a set of lines as a function of the plunger, and a slight variation depending on this split gate, as we call it, in the middle here, but not very much. And then we look at the second barrier, the right-hand barrier, this one over here, and do the same experiment. We can see some lines similarly that depend on what we're doing in the right-hand side. The crucial question is what happens when we do something on the left and measure on the right. But comparing the 2 tunnel barriers in their own right, doing their own thing, so we set up, this is the left barrier, its oscillations, right barrier has its own oscillations, different periodicity, but the same sort of slope and so on. That matches what we saw in the previous device. So there, effectively, we got 3 sets of oscillations from 3 different tunnel barriers. So now we can set up the 2 barriers simultaneously to both allow tunneling. I mean, in the previous case, when we were looking at the right-hand side, we made this barrier very thick, so there was no chance of tunneling out of that one. And so now we measure both left plunger and right plunger gates. That's the two gates above each of the tunnel barriers. And to make sure that we can differentiate or filter with respect to either of those two, we sweep the two gates simultaneously. So that's why you've got a diagonal plot here. So we're actually sweeping diagonally here. So we've got the information as a function of either of the gates. And so the left-hand plot here shows the left tunnel barrier current. The right-hand one is the right tunnel barrier current. So here, as a function of right plunger, there are no oscillations. So the left region of the device has no knowledge of what's coming next, what happens downstream where the saw reaches the right-hand plunger. So there's no coupling electric fields. So even though these two are a few microns apart, the electric field from the right-hand side is not very significant at the left-hand side. So we just see oscillations as of, I'll differentiate this here, I'll filter it. So you see the oscillations, they're totally horizontal, so they only depend on the left plunger gate. Whereas on the right, we see some horizontal ones, so we see strong vertical ones that depend on the right plunger, but we also see horizontal lines that match up almost with the ones on the left. So that shows us that we're managing to set up some oscillation on the left-hand side, and it persists as it goes through the middle of the device, so this region here, and is still oscillating when it gets to the right-hand device here. And so that shows that we can set up oscillations, and we now need to be more creative about finding things we can do with such a device. Essentially, it's a charge qubit, if you like. It's oscillating backwards and forwards. You could think of that as left or right, or ground and excited states, and so on. We can think about what's the coherence of this. We haven't got many data points. We know it manages to travel, the saw manages to take the electron a distance of about 1.5 or 3 microns. I mean, each of the tunnel barriers is about 1.5 microns long. So we've got this sort of uncertainty in what the distance between the two tunnel barriers is. But that corresponds to a time of order 500 picoseconds. So that's the sort of coherence, charge coherence time that we get. Okay, so those are the two major things I wanted to just illustrate we can do with saws. And so just to show the sorts of things we're trying to do at the moment, I've mentioned we would like to convert electrons to photons, so electron quantum information to photon quantum information ideally. So we have to have holes and electrons in the same wafer. And unfortunately, when you're growing with MBE, you can't put doping in different places, different doping in different places. So you're stuck with an N-type wafer or a P-type wafer. So the only solution really, or the best solution, is not to have any doping in at all, and then to induce electrons in different regions, or electrons in one region, holes in another. So for that you need different ohmic contacts for electrons and holes where you can induce. So getting induced devices to work is always a bit complicated. Not many people do it. We've been doing it for a long time, but every so often it gets difficult again because of different requirements, or just processing goes strange, as my students will tell you. And so but in principle, and some of the time, we can make reliable ohmic contacts for electrons and holes simultaneously. And so we have a region where we have electrons, and that's induced by gates over the ohmic contacts. That takes electrons towards the center of the device. We then switch over to having a surface gate, as we call it. So it's a gate on the surface of the gallium arsenide, which then induces electrons near the middle. So you've got complete control by having two inducing gates. One induces over the ohmic contacts and one induces near the center of the device. We can just play with the gate voltage in the center without worrying how the ohmic contacts are behaving, because they have then been set up to be reliable. So we have a source, say, which could be N-type or P-type, depending on the type of ohmic contact or the voltage we put on these gates, and a drain, which is likewise, it could be N or P-type. And then we can have other gates, and we can play. We've done a lot of modeling to see what sort of potentials would be useful here and what sort of distances we can get away with. So we know we need to try to keep this distance between the source and drain to be pretty small, smaller than a wavelength probably of the saw. Our saw wavelength is 1 micron usually for a 3 gigahertz saw. And then we try and squeeze the channel from the side gates, or actually use the side gates to pull electrons out of the source. And so if we operate as an end-to-end device, so electrons on both sides, we see quantization. So we can actually, in one of these devices, we managed to see the EF plateau, or hint of it, and a 2EF. And it survives whatever gate voltages we put on it. But we can also go for N to P. So now this is N and this is P. So there are electrons here, holes here, and we can pump between them. So there's a big slope, as I showed in one of the schematic diagrams, between the conduction band in the electron region and in the hole region. And so we can forward bias the device to try to equilibrate those, or get closer to putting them in the same height. But you don't want it to be exactly flat band, because then there'd be a lot of current flow just thermally excited and whatever. So we get close to that, and then the saw should be able to drag electrons up that slope. And so that's the forward biasing. The saw can then pump electrons, so we can see a current flowing. And as of Sunday, that we could see where the light was coming out. Unfortunately, it's coming down here, not coming out in the PN junction here. So the problem we're having at the moment is just making the electrons recombine under the drain. Unfortunately, the drain is where it attracts holes, so obviously it repels electrons. So we've tried etching around this region to try to keep the electrons in the right place, but we've got further development to do on that to get it right, and I hope we will. So having light coming out miles away just illustrates that once the electrons have got out away from these holes, there are no holes to recombine with, and so they eventually find some near one of the contacts down here and so on. But otherwise, they've got a very long lifetime in the conduction band in the intrinsic regime. So that was taken using a small optical cryostat working at somewhere just above 4 Kelvin. But we have a helium-3 system, and we've constructed a microscope that is inside the helium-3 system. So it's at temperatures down to 300 milli-K. We have an optic fiber and a piezoelectric stage at low temperatures that can resolve a spot. So if light is coming out of a region in the chip, it will be collected from 1 square micron at a time. So it's pretty tedious when you're trying to find that spot, which is why in that cryostat we couldn't find it coming out of the wrong place. But, my student Sukan Xiao has been looking very carefully around all the interesting parts of the device and not seen anything, unfortunately. So now we know why. But we'll improve that. So in principle, even with a fiber, you can preserve the polarization, or at least calibrate the polarization change as the light goes through the fiber. So we should be able to measure the polarization behavior of the electrons, or the photons that come out, as we change the polarization of the electrons. And we scan the lens assembly rather than the sample holder, and that allows us to have a heavy sample holder with coax cables and so on. So that's quite convenient. And as I say, it's available for other applications. So if anyone wants to get to low temperatures with their optics, perhaps they should come and talk to us and see if we can help. So I've just put this slide. It's quite a lot of information on it, so don't worry about it. But I just wanted to sort of highlight the fact that although at the moment we're just planning to measure the spin, so read it out, so we're not trying to keep in a superposition of spin states of the electron, in principle it is possible to do so. So Kasaka in Japan showed that, so there's a whole set of references here, that if you have, so what you want to do is convert a superposition of electron spin states to photon polarization states. So it's the Poincare sphere for photons versus the Bloch sphere for electrons, and you just want to do a one-to-one conversion. But unfortunately, if you have an electron of upspin or downspin, when it recombines with a hole, it has to find the right hole to recombine with. So up electron with down hole, down electron with up hole, for example. And that gives out these polarized photons. But the trouble is the holes then have some information, or they did have before, and so now they've been destroyed. There's information in the system that they have, so they decohere very rapidly. Another way of thinking of it is if you've got 3 particles and they all supposedly know the information, that means you've cloned the information by going from one electron to a hole or missing hole and a photon, so that's not allowed. So you can't do complete conversion of the qubit from electron to photon without preparing the holes specially. So the idea is that Jablonowicz had originally is that you should polarize your holes in a sort of left-right basis. So try and get all the electrons to have a right spin here, all the holes do. So now a hole in the right state here is a combination of up and down. So when the electron in its combination of up and down, so alpha up plus beta down, recombines whichever it is, whichever of those it is in, can recombine with the same hole because the hole has a combination of these states in it, or its corresponding states. So really what you're doing is put this V-shape transition here, that it doesn't matter which of those, they're still recombining with the same hole. So the trick is to have the holes spin split, and unfortunately the only way to do that is to have a light hole. The heavy holes don't spin split enough, but to engineer the wafer so that there's no spin splitting for the electrons, so no G factor for the electrons. And that seems to be possible if you get a very narrow quantum well with particular aluminium ratio. But you need to use the light holes.
Would that mean that you only in 50% of the time can recombine and the rest of the time you are stuck? Because imagine, say, alpha equals 1, beta equals 0, this in this case. It's just up. And so there is a superposition of up and down for the whole, and it can only recombine with one half of the superposition.
Well, I think the hole is it's happy to combine with an up state with 100% probability, or to combine with a down state. Put it this way: there are lots of holes there. I don't think that really matters, but the electron can find a hole to recombine with. And well, if it doesn't recombine immediately because that hole in its superposition, as you're implying, isn't in the right, has a 50% probability of recombining, then it will just have to stay there until it does recombine with another hole. But when it does recombine, it's recombined with a hole in this state. And so there's no information left about what direction the hole was in the first place, because it's all in that direction. So that way you can get, and Kosaka has demonstrated that you can get perfect transmission conversion from photons to electrons or electrons to photons. So I think it's just something worth bearing in mind. But my time is up, so I'll just put up my conclusions. We've got dynamic dots. You can do lots of interesting things with them and demonstrate coherent oscillations and so on. Thanks for your attention.
So, in the single barrier tunneling experiment, you said it amounts to doing a weak measurement?
Yes.
So, could you say a little more about that?
Okay, I'm sure there are more specialists here who know more about weak measurements, but I think the point of a weak measurement is that you can measure something that doesn't disturb the state, because you're not measuring that property itself, you're measuring some other property that tells you something about the system. So here we're measuring the fact that it bounces a number of times, so effectively the frequency of bouncing, but we're not sensitive to exactly where it bounces. And so in that sense we're not disturbing the wave function very much. A small probability of tunneling, so it's maybe 1% probability of tunneling out, something like that. So it's making a very small disturbance to the system. So it's not exactly this type of weak measurement that other people are doing, but it's an interesting type of measurement. Mm-hmm.
So in your diffusion slide, you say that you are able to initialize an oscillation phase in this double barrier experiment. But for me, it's difficult to see where the difference is between just the law of current conservation and the oscillation phase. Because when an electron leaves via the first tunnel barrier, then of course I cannot detect. I have like less current possible at the right tunnel barrier.
Current conservation exists. Yeah, we know we have current conservation. So anything that goes out the first one is lost, and so we don't measure it in the second one. So we're sort of taking that into account in looking at the how much comes out of the second barrier. So if what you're asking is, does the fact that it's oscillating in how much goes out the first barrier cause the oscillations that we see in the second one? We've taken that into account, and it doesn't cause it. So it's an effect, but we can account for that, and we still see these oscillations.
So when I would say I initialize the oscillation phase, I would expect like of the lines coming without cost, or I would basically. I would basically have like a different slope for the second phase maybe on the diagram, depending on the openness of the tunnel barrier.
Yes, I'm not sure of how many different things we tried, but I mean, certainly the tunnel barrier was open. I can't remember how much we varied it, but the slope. I mean, there's no slope on here. It might be the spacing of states that depends on the size of the dot, and therefore, but the size of the tunnel barrier. But I think this spacing here is the same as that spacing there, so it's definitely a one-to-one correspondence. The phase is different. So I think it does depend on what we see on the right is linked to what we see on the left, and we've done various experiments with tunnel barriers. It's just a number of years ago now, so I can't remember exactly what we did, but I think that works. But we did have to take account of the current that's lost on the right hand, on the left.
Do you know have a guess what limits the spin lifetime in these dynamic quantum dots?
So with the dynamic dots, what you can't do is the sort of Hahn-Echo type measurements. So we know that in gallium arsenide we have nuclear spins, so that's going to be what limits the spin lifetime probably. So in a static dot, you can then try to take account of the fact that the nuclear spins change very slowly and do various pulse sequences to get them back to where you started. Here we can't do that because the electron's moving, so it sees a different set of nuclei at each point. But on the other hand, it benefits from what's called motional narrowing, so it's seeing lots more nuclei, and so the averaging from that gives a smaller field and therefore a slower change in that random field. So it is a limitation, but it's over these sorts of distances, I don't think it's too significant. But it means that gallium arsenide is not the ideal material for doing quantum computing, unfortunately. But it is a limitation that we can't overcome here. There were suggestions that the surface acoustic wave would see, because the electron's moving, any fluctuations in electric potential and electrostatic potential would be converted to magnetic fluctuations, and that would give an extra dephasing. Well, I haven't got any evidence for or against, but I think that's possibly less important than the nuclear spins.
You could have just the inverse effect, you could have a motional narrowing due to the motional narrowing of the amount due to the...
That's what I was saying just now. I mean, there should be motional narrowing, and so I think motional narrowing gives something like a factor of 100 increase in the time, according to my simple calculation, but you may know more.
Okay, time's up, so we can thank the speaker again.